Hello everyone, welcome again to our webinar on modeling thermal stresses with COMSOL Multiphysics. My name is Arpad Forberger and I'm an application engineer at Gamax Laboratory Solutions Ltd. And today we are going to take a look at the basics of how COMSOL is used for modeling thermal stresses. I will walk us through a model to give you a chance to see the software up and close and see how it might help you in your work. If you have never used COMSOL before and you want to learn how it works, my presentation today should help answer those questions. And today's agenda include an overview of the software, what kind of modules are available for different purposes, how the model looks like, what is it about. And during a live demonstration, I will set up the model from scratch, step by step, and at the very end I will summarize my presentation and I will give you some additional resources that you can read and watch videos and recorded webinars. COMSOL is a multiphysics modeling, simulation and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to solvers and post-processing to putting together a custom-built application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. The model we will look at today solves for Joule heating coupled to structural deformations. Once you have completed your COMSOL simulation, the software allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing for external softwares like the LiveLink for MATLAB. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. And today's webinar includes the functionality from the AC/DC module, from the structural mechanics module and the heat transfer module. So these three modules will be used and required to build up this model. We have several different components to the COMSOL software. Right now we are looking at the model builder in COMSOL desktop, which you will see live in a few minutes. The model builder contains the tools for controlling physics, mesh, materials, and study settings. Highlighted in this image is the section of the ribbon that gives you access to the application builder portion of the COMSOL desktop, which contains the tools for building a customized user interface around your model, or what we call an application. And because I mentioned earlier, once you are finished with the simulation, you may want to be able to share the results with a colleague or a customer without sharing your entire model. The application builder will let you build this user interface around your simulation, and then you can share it to others. To others who doesn't have COMSOL installed on their machine, you would use a local installation of the COMSOL server, which makes the app accessible either through a COMSOL client or a web browser. What's really powerful about this is that the person you share the application with doesn't actually need to have a background in COMSOL, numerical simulation, or the relevant physics. For instance, you might share it with a colleague who doesn't have your modeling knowledge, but who can use your app to run quick virtual tests and check different designs. Here you can see today's model definition. So we will use two copper pieces, they are bounded together, so they are in physical contact. They are initially in an overlaid position, so it will give us an initial contact pressure between the contact surfaces, which describes and which has an effect on the thermal conductivity and electrical conductivity between the two pieces. We will have, from the electrical side, we will have a ground from one boundary, and we will apply 1 millivolt voltage on the other boundary. From the heat transfer side, we will have heat flux to the ambient temperature, and from the structural mechanics side, we will define fixed boundaries on both of these tips, and the contact pair will be defined during the model setup. And now we can jump into the COMSOL desktop and see how to set up this model step by step. For this model, we will build a three-dimensional geometry, and we can use a predefined physics interface for these coupled physical phenomena. So if we go down to the structural mechanics branch, we can find this Joule heating and thermal expansion subnode here. Here on the right hand side you can see some description, what is it about and what kind of physics interfaces will be used during the model. So I can add this to our 3D domain, and here you can see 3 separate physics is added: a solid mechanics interface, a heat transfer, and an electric current. And we have this multiphysics node, one for a thermal expansion to take into account the thermal expansion of the copper plates, electromagnetic heat source to take into account the Joule heating effects, and 2 temperature couplings. So we can simply map the temperature field both to the solid mechanics and the electric currents interface, because temperature material properties can be temperature dependent. Next we can add the study. We will use a simple stationary solver here. To speed up the computational process, I will import the predefined geometry. So we can import our geometry. It's a contact switch. Okay, so here you can see the model itself. As explained previously, here in the middle they are in an initial overlap. So here these 2 parts overlap, so it will give us a very nice initial contact pressure between the 2 surfaces. So first let's define the contact pair for the structural analysis. So these pairs can be found under definitions, pairs, contact pair. Okay, and from the source we can select surface 12 and 15. Oh, sorry, I forgot to change this to an assembly. We don't need pairs. Okay. So if we go back here, we can simply remove and select again 12 and 15. So they are the one portions of the lower part, and the destination boundaries are like 25 and 28. So they are on the upper part. So they define this contact pair for the structural analysis. For the materials, so we will add the material from the built-in library. So if we go into the built-in section, we can select copper. Okay, by default this material is assigned to all of our domains. We have 2 domains, we have 2 parts in the assembly, and here you can see the green tick marks where all of the required material properties are available and set up. So if you need more, if you need a custom function, you can simply click here, delete and overwrite with your own function, with your own table. It can be even a MATLAB function that defines a material property. Literally wherever you can click in COMSOL Multiphysics, you can delete and overwrite and put your own value there. It's quite easy to do that. So that's from the geometry side, and from the material side, then we can go to the physics interfaces, solid mechanics. From solid mechanics we will have fixed boundaries, so we will fix two parts of the boundary. So that will be 4 and 5 from one part, and 34 and 35 from the other part. This means we fix the inner boundaries of these copper parts. We will add the symmetry boundary condition to these boundaries, because we use only half of the geometry, so we can reduce computational cost. And we can add the contact pair, so we can find this under pairs. There are much more. For this purpose we will add the contact pair. So here we select our contact pair that was defined previously, and that's all. That's for the solid mechanics interface. If you want to take into account the thermal expansion of the boundaries of the constraints, that's also possible on COMSOL. So you can even right click on the fixed constraint and you can select thermal expansion. That's also available. So if you need more sophisticated boundary conditions, that's another option to improve your model setup here. Move on to heat transfer. We can add the same symmetry boundary conditions for the two plates, 2 and 22, and we can add the heat flux to the outer boundaries. So we can select all boundaries except the inner ones and the symmetry ones, and we can set up a heat transfer coefficient. It can be a constant value, like let's say 2 in this example, or you could use these 4 options, whether it's an external or an internal, natural or forced convection. So you can more modeling options here than just putting a constant value, scalar value here. Okay, and because this conductivity, thermal and electrical conductivity can behave and can depend on the contact pressure between the two parts, we need to add the pair thermal contact. So under pairs, we can select pair thermal contact. We select that one pair that we defined previously under definitions. So that's the contact pair we defined previously here. And then here you can see the options. So you can play with the surface roughness. Now it's a constant value, but it can be a function, so you can create parametric sweeps. And the most important thing, that the contact pressure is not a constant value, but it's fed from the solid mechanics interface. So we simply switch this value to the contact pressure solid interface. So whatever contact pressure is calculated in the solid mechanics interface, it's automatically paired and fed into this boundary. So it will use and it will behave like in a real device. That's for the heat part. We can move on to the third physics interface, electric currents. So in the previous figures you have seen that we need to add the ground node and an electric potential. So we will add the ground node to boundary 34, that's here. So it will be 0 potential, and we will add 1 millivolt electric potential here at the other boundary. So we put 1 millivolt here. Okay, and like in the heat transfer interface, we can add the pair electrical contact. We select that one and only contact pair, and as previously, like in the heat transfer interface, we can select that the contact pressure, it's not a scalar value, but comes from the calculated from the solid mechanics interface. So now we couple the 3 physics interfaces. That's how it's done in COMSOL Multiphysics. One little thing is missing, so we need to adjust the mesh a little bit. because this default is not fair enough. So in the contact pairs, in the contact domains, we need a really nice and fine mesh to get a nice converged solution. So we edit the physics-induced sequence, and if we go to the free triangular, of course, COMSOL automatically detects that these surfaces are the contact pairs, so we can set up some size settings here to make it finer. So maximize the element size here, -4. So we get a much nicer mesh resolution here, and we can look into the model. So if I remove some surfaces, we can easily look into the model. So now we have much finer mesh at the contact pair. Okay, so that's from the physics setup, and for timing purposes I will open up the solved model. So it takes about 5 minutes to be solved. So I jump over these 5 minutes and open up the solved model to demonstrate the solutions to you. So this is the same model but with the solved, with the solutions. Here we have a stationary solution. You can see that all tick marks are there. So we are solving for the 3 physics at the same time with all the multiphysics couplings. And here we have the predefined plots. So these are the automatically default generated plots. For the solid mechanics interface, we have the Mises stress in pascals, but we can change this quite easily to megapascals. Just overwrite the unit to megapascals and maybe put it down in the bottom instead of the right version. Okay, show maximum and minimum values. Okay, so this is the Mises stress. We can go to the other default plot, which is the electric potential, and yes, we can check indeed. We have 0 at the ground and we have 1 millivolt, yes, on the other part. So we have a continuous evolution of the electric potential on the copper domains. Temperature plot. Okay, change this to another type of plot, to, let's say, heat camera, and we can change the unit to, let's say, to Celsius. Okay, so from room temperature we are up roughly to 25 degrees of Celsius. So based on this 1 millivolt increase, we have a 5 degrees of Celsius increase compared to the initial temperature. So you can use this plot to check what kind of temperature increase would your device exceed if you apply this kind of electric current through your device. And the last default plot is the isothermal contours. But we can generate custom plots. So we can add the 3D plot group and let's say add the streamline plot of, let's say, the current density, current and charge, current density, and let's do with a uniform density to make it nicer. Okay, so this is the current density like a streamline plot, but we can add more colors to make it nicer. Okay, we can play with the scaling factor, we can make it a bit lower, and of course we can add the color expression, let's say colored by the displacement, whatever, or we can color by the current density norm. That can be much nicer here. Let's say go to electric currents, current density norm. Okay, so that's one thing here. So we can easily do a streamline plot colored by any kind of built-in variables. So if you don't know the name of the variable, that's not a problem. So you can always go to these little triangles and you can go to component. Which physics interface are you interested in? Let's say it's solid mechanics. Then you can select a strain or stress, whatever your need. And then, because it's based on thermal stresses, so we wanted to plot the thermal stresses, like here in the first default node. We can add another plot, let's say, to plot the strain rates of these. So we can add a new 3D plot group we can select, let's say, from the solid mechanics interface a strain, let's say a volumetric strain. That's okay. So this is how the strain looks like after applying 1 millivolt difference between the two parts of the copper part. And if you want, you can add the deformation quite easily. COMSOL will automatically apply some scaling factor. Yeah, it's a bit big, but if you can override to, let's say, to 1 to see the exact deformation, you can see the final plot here. So this is how it looks like, and we can add the max plot. That's the last thing I want to show it to you. Max mean surface, let's say, to plot the maximum displacement in millimeters. Okay, so we can look that, yes, the maximum displacement is 0.2 millimeters, and it's available at the very tip of the copper part of this one. So it was a bit fast for some of you. That's not a problem, because we are recording this webinar, so you will be available to watch it later and read more about the model itself, because we will include detailed model documentation in the follow-up email. And if you need more information about the model or any kind of COMSOL possibilities, what kind of modules are available, what kind of physics can be solved with COMSOL Multiphysics, feel free to visit our website or write us directly to our company email addresses. You can request a free trial version, that's also possible. And during the trial period you have tech support, so if you need some help and assistance, we are more than happy to assist you through this trial period. And you can find much more models at our website. Now I close up my presentation, and thank you for your time, and see you at our next webinar.